We are further continuing with the concept of gravitation, and our context of discussion is geostationary satellites. So, what basically is a geostationary satellite? There are certain important points about the geostationary satellites. Number one, the spin time of Earth and the spin time of geostationary satellite is the same. That is nearly 24 hours. The another thing is important about the geostationary satellites, that is the height of the satellite from the circumference is about 36,000 kilometers, whereas from the center of the earth it is nearly 42,000 kilometers. Moreover, the geostationary satellites they appear stationary from the circumference of Earth to an observer standing on the surface of Earth. Another thing important about the geostationary satellite that they are used for the radio communication. So radio communication means audio frequencies or certain typical frequencies are received by the satellite and transmitted to the different stations broadcasting portions. Now, geostationary satellites can be explained like this. The geostationary satellites, which are stationary with respect to an observer on Earth, are termed as geostationary satellites. These are also known as the parking satellites, and the orbit in which the geostationary satellite is existing, that is called the parking orbit. From the parking orbit, the radio communication can be carried out, or the television communication that can be carried out from the parking orbit. The direction of rotation of the geostationary satellite is always from west to east, and the time period is 24 hours, and its angular velocity is same as that of Earth, revolving around its axis. This I have just started before starting, that is before explaining about the function of a geostationary satellite. Geostationary satellites can be launched just above the equator, and this I have explained earlier that the distance of the geostationary satellite is nearly 42,000 kilometers. So the radius of orbit of geostationary satellite, that is R, is 42,000 kilometers, and its height above the surface of Earth or from the circumference is about 36,000 kilometers. This indicates that 36,000 kilometers is the height from circumference, and if 6,000 kilometers is nearly the radius of Earth, the net distance becomes 42,000 kilometers from the center of Earth. So a point about 42,000 kilometers above the center of Earth is called the parking orbit or geostationary orbit. So now this is indicated in a figure, that is satellite moving from west to east, and this is what is responsible for the sunset and sunrise on the Earth. Now there are different values of satellite. I have already explained, but let us first of all review all of these points. Number one is the angular velocity is omega, that is calculated by 2 pi r over v. Now we put the values of r and v, and pi can be taken as 3.1 and 3.41 or 3.14, and by calculation it will become 7.1 10 to the power minus 5. So angular velocity is indicated in radians per second. Now we have to go through the linear velocity of the geostationary satellite. That is, geostationary satellite is spinning with the same velocity as that Earth. So the spin velocity of the geostationary satellite is 3.1 kilometers per second. It means that during the spin in 1 second, it covers the circumference of 3.1 kilometers. The time period of the geostationary satellite is 24 hours. We are repeating it, however, I have explained earlier. Height above the Earth's surface is about 36,000 kilometers approximately, and from the center it should be 42,000 kilometers. Again, the figure is indicating the spin of geostationary satellite, that is from west to east, the same as that of Earth. Now we come towards the angular momentum or angular displacements. At time t, the angular displacement of Earth and geostationary satellite is the same. That is the spin time. That is 24 hours. And angular momentum of satellite is conserved. There is no loss or gain of the angular momentum. Normally it is given as L is equal to mvr, or sometimes instead of L we use J. J can be written as mvr, where m is mass of the geostationary satellite, that is supposed to be comparatively quite less, and r is the radius. V is the velocity of spin. So J, that is angular momentum, that is given by mvr. Now mr is kept outside the root sign, and for V we will put the value, that is g re square. G is acceleration due to gravity, r is supposed to be the radius of Earth. Now this can be further written as m into, and for r we can put the value re under root gr. Re is the radius of Earth, small g is the acceleration due to gravity, and r, that is the radius, and it can be written as m into under root gme over r. Satellite behaves like a freely falling body towards the planet. The satellite revolves around the Earth in an orbit with Earth as center of the focus. Now, we'll take a concept of the packet as we make the packet to fall on the surface of Earth. That is, if a person is standing on the surface of Earth and he has got some packet of some material, we find that if that person is releasing the packet, it will come towards the surface of Earth. Now, if a packet is released from the satellite, it will not fall on the Earth, but it will remain revolving in the same orbit with the same speed as that the satellite. And that packet, which is released from the satellite, will behave like an artificial satellite. No gravitational force of satellite is used up for providing the necessary centripetal force. Due to gravitational force, the effective value of acceleration due to gravity, that will become zero. As a result, effective weight becomes zero, so the person sitting in the satellite will enjoy weightlessness. So if a person is in the space, the person in the satellite will enjoy, that is the weightlessness. However, the person has weight, but acceleration due to gravity is zero, therefore the weight, that is mg, m multiplied by 0, so that will become 0. So the person will enjoy the weightlessness. So we will find that in the satellite, the person will just float like in water. Man experiences this weightlessness condition only when weight of the satellite is very less. Therefore, gravitational effect of the satellite is negligible. Moon is a satellite of Earth, but a person on the moon does not feel weightlessness. The reason being, that is, mass of moon is comparatively more. However, the value of acceleration due to gravity on the surface of moon is 1/6 that of Earth. So person who is weighing 9 kilogram on the Earth will weigh only 9 multiplied by 1/6 on the moon. So, once more I will repeat, moon is a satellite of Earth, but a person on moon does not feel weightlessness. The reason I have already explained. The reason is that the moon has large mass and exerts gravitational force on the person. And this is the weight of the person on the moon. Normally, the weight of person on the moon is 1/6 that of Earth. because the gravity is one-sixth that of Earth. Now, the artificial satellite having smaller mass does not exert gravitational force on the spaceman.